So next point is about the ratio. We have to treat the ratio of two sequences, of two convergent sequences, and to see what happens to the limit. And so we start with a lemma, preliminary lemma. I think it's the first time I use the word lemma in this course. What is a lemma? Lemma is a sort of introductory theorem. Okay? It's a technical result which is not important in itself, but it is useful to prove important result. This is the meaning of the word lemma in this context. Okay, so the lemma says let Bn be a non-zero, it is a non-zero sequence, and suppose that Bn converges to a number k which is non-zero too. Okay, I have to specify that k is non-zero because you know there are non-zero sequences that converge to zero, like 1 over n. Okay, in this case, it is not the hypothesis. And then the sequence 1 over absolute value of Bn is bounded. Okay? We prove that a convergent sequence is bounded. Here we have a convergent sequence which is not vanishing and whose limit is not zero. Then the sequence of its inverses is bounded too. Okay? Let me give you first the idea of the proof. The pictorial idea of the proof, as usual, I like very much to give you pictorial ideas because, in my opinion, they help you to follow the proof and to understand what really happens. So here we have 0 somewhere, and the sequence Bn falls far from 0. At some point there is a limit k, for instance here, and the sequence sooner or later concentrates around k. Okay? What is the key idea? The key idea is that Bn remains distant from 0, so at a finite distance. So Bn remains distant from 0, and so 1 over modulus of Bn remains bounded. This is the idea. As usual, the idea can be quite simple, but the proof can be quite complicated, as usual. Here we don't have to prove a limit, but the starting point is always the same. So let epsilon be a positive number. Then there exists n bar such that whenever n is larger than n bar, we have that Bn minus k is less than epsilon. Okay? So we are interested on modulus of Bn, and we have that modulus of Bn minus modulus of K. Here we use the second triangular inequality, and we know that this modulus is less or equal than Bn minus K in absolute value again. So this is the second triangular inequality. So the conclusion is that also after some n bar, namely eventually, the distance between the sequence of the moduli of Bn is at a distance from the modulus of K which is less than any epsilon. Okay? Therefore, by definition of limit, we have that the sequence of the absolute values of Bn converges to the absolute value of K. Okay? And moreover, we know that Bn, being convergent, absolute value of Bn is bounded. Okay? So since it is bounded, it has an infimum which is non-zero. So here we have consider M, which is the infimum of the all Bn's. Okay? Now, we have that M, this little m, is different from 0. Indeed, what happens? If M is a minimum, then there should be an element of the sequence absolute value of Bn, which is 0. And this is forbidden by the hypothesis. It's against the hypothesis. This is the first observation. And the second observation, if it is not a minimum, so if M, this is more delicate. But just an infimum, then this is, and M is equal to 0, then for the characterization of the infimum, for every epsilon larger than 0, there should be a Bn such that 0 is strictly less than modulus of Bn, strictly less than epsilon. Okay? But at the same time, there exists an n bar of epsilon such that for every n larger than n bar, for every n larger than n bar, one has that modulus of k minus epsilon less than modulus of Bn less than modulus of k plus epsilon. So then think of it, but 1 and 2, these two relationships, 1 and 2 can hold together if and only if k, modulus of k, is equal to 0 against the hypothesis. Let me be pictorial in explaining that, because what I'm saying is that here you have 0, the sequence falls away from 0, then there is a limit, k, which is non-zero, for instance here, sequence concentrates here. Just pick if 0 is the infimum of the modulus of the sequence, then take an epsilon, whatever epsilon larger than 0, there is an element of the sequence that falls here. This epsilon can be chosen smaller and smaller. At the same time, after some n bar, the sequence must concentrate here, around k. So these two facts cannot hold together unless k is equal to 0. This is because epsilon can be chosen always smaller and smaller. Okay? I know this is delicate, so think a bit of it. And the conclusion is that, so, for every natural m, you have 0 less than m, less than modulus of Bn, and this means that 1 over modulus of Bn is less or equal 1 over n. We need to know that m is different from 0 because here we have to inverse m. Okay? And so, okay, the conclusion is that 1 over modulus of Bn is upper bounded. And so now we can give the last theorem, the theorem about the ratio of two sequences, two convergent sequences. Here you have an that tends to L, which is a real number. Bn converges to k, which is in R minus 0. Bn different from 0 for every n. Then the ratio Cn equal to an over Bn. This is another sequence, the sequence of the ratio, converges to L over K. So again, the statement can be summarized, formally summarized, by saying that the limit of the ratio equals the ratio of the limit of the limits. Okay, so the proof is easy. It's quite similar to the proof of the limit of the product, and this is the proof. And so let epsilon larger than 0 be arbitrary, and now since an converges to L, then there exists a number n1 bar such that whenever n is larger than n bar 1, an minus L is less than some epsilon prime to be defined later. As we already did for the proof of the limit of the product. And analogously, since Bn tends to K, then there exists n2 bar such that whenever n is larger than n2 bar, we have that Bn minus K is less than the same epsilon prime. So since we want the two relationships hold simultaneously, we define n bar that equals the maximum between n bar 1 and n bar 2. And now we pick n larger than n bar, and we conclude that the distance between the ratio sequence Cn minus L over K is equal to An over Bn minus L over K. Now we use the same denominator and we obtain Ank minus Bn times L divided by Bnk. And now again we add and subtract the same quantity, but this time what will be useful to us is An Bn. So we first subtract, then we sum An Bn minus Bn L, everything here divided by Bnk. And so here we use the first triangular inequality for the numerator, so we have Ank minus An plus An minus Bnl. Everything here is divided by Bnk. We use the other property of the absolute value that says the absolute value of the product is the product of the absolute values, and here we have An times Bn minus K plus Bn times An minus L divided by Bnk. Okay, now we use that An and Bn are convergent, so they are bounded. Then we have that An in absolute value is less than some A, Bn is less than some B, and we can choose A and B larger than 0. Moreover, since Bn is always different from 0 and also K is different from 0, for the previous theorem we know that 1 over the absolute value of Bn is bounded. So we can say that 1 over Bn is less than some M, capital M, okay? Here I change a bit the notation with respect to the previous theorem when I used 1 over small m, okay? This is 1 over capital Bn, 1 over Bn is less than capital M, and so we end up with therefore Cn minus L over K. This is less than A Bn minus K plus capital B An minus L. Here there is K in modulus remaining here, and 1 over Bn is less than M. Okay? Now we recall that we used this definition of n bar, and we chose n larger than n bar in order to let these two inequalities hold together. So now we use those inequalities, and we find that this is less than A epsilon prime plus B epsilon prime divided by modulus of K times M. So this is equal to A plus B times M divided by modulus of K epsilon prime. So now we can choose epsilon prime, which is epsilon times K divided A plus B M. Of course, all these guys here are positive. Okay? Remember that A, B, M, K are positive. So epsilon prime is larger than 0, and this is what we want, what we need in order to use the definition of limit and say that the distance between the sequence and the limit is eventually less than epsilon prime. Okay? So this is epsilon prime, and therefore Cn minus L over K is less than epsilon. And so what did we prove now? We proved that eventually, so after some n bar, when n is larger to some n bar, the distance between the ratio sequence and the ratio of the limits is less than epsilon. So by definition of limit, we have that Cn converges to L over K. Okay, and this is what happens now, and the proof is complete. So, and now that we have this algebra of limit, and which is ready, and with the algebra of limit we can compute many limits, so in particular we can deal with many convergent sequences. And let me stop this recording and start another one with some